Oh, sorry. So Gavin and I met 2 or 3 years ago doing advising, and of course the question was like, how can I become a paleontologist who hunts dinosaurs? And that of course doesn't happen at LSU anymore. So anyways, yeah, we then back and forth, and he finally settled on a research project with me after some back and forth, but I think he came up with really, really interesting results on a problem that has stomached me and John Haynes for a while now. And I want to already thank you, Adam, for all your input and advice, because it's more and more venturing out of my comfort zone and also out of John Haynes' comfort zone a little bit. But as we will learn from Gavin today, it's a very important question that we're trying to address, and that is whether Taconic orogeny down in the southern part of Alabama is actually consistent with previous models that have had some different ideas how the Appalachians actually started forming down in Orogehy. And without further ado, I'll hand it off to Gavin. Now, before I do that, rule number 1, so what we're going to do is we're going to have the presentation, and then there's going to be questions from the audience, so fiancés can grill at will. After that, we're going to ask you to leave, and then it's the committee to ask questions. But yeah, you will get your special time with him.
Okay.
Okay, go ahead.
All right. Thank you, Dr. Herman. As he said, and as most of you know, my name is Gavin, and I will be talking about the work that we've done with characterizing the Taconic orogeny through geochemical analysis of the Deicke potassium bentonite. And the question we'll be asking is, do we have the Taconic orogeny backwards? So, the Taconic orogeny occurred in the Ordovician period, and it was a convergent mountain building event between the continent of Laurentia and the Iapetus Ocean, and it led to the uplift of the Appalachian Mountains in eastern North America, and it caused extensive volcanism throughout the eastern United States, and that volcanic ash from those eruptions is preserved as potassium bentonites today. So the controversy surrounding the southern margin in particular of this orogeny is that it's conventionally been described using the back arc Sea of Japan model to the left of this figure, where the Iapetus Ocean slipped beneath the Laurentian continent and caused back arc volcanism on Laurentia. But there is an alternative model that's been proposed in previous work. For the purposes of this study, we're going to call it the Timor model, as coined by Dr. Herman and Dr. Haynes in their previous papers. And so that model is characterized by island arc collision with the continent of Laurentia, where the continental shelf subducted beneath this island arc and caused that volcanism instead of back arc volcanism, the reverse orientation. And so the potassium bentonites from these eruptions form the Hagen potassium bentonite complex. They were formed from the devitrification of volcanic ash after the eruptions and the introduction of non-exchangeable potassium through diagenesis and burial. And so the Hagen potassium bentonite complex comprises several different individual volcanic ash layers, but the focus of this study was on the Deicke, is specifically a Deicke sample from Red Mountain Expressway in Birmingham, Alabama. And these are at the bottom are the exact latitude and longitude coordinates from where this sample was collected. And this figure to the right shows the stratigraphic relationship between each of these layers and their broader stratigraphic context throughout the Ordovician. And so this is a figure with the first panel A is a paleogeographic reconstruction around the end of the Taconic orogeny, about 446 million years ago. This reconstruction is consistent with the conventional model of the Sea of Japan model, with the Iapetus Ocean subducting beneath the Laurentian continent, producing back arc volcanism. And the approximate sample location is denoted by the green arrow, sort of pointing to Birmingham. And then panel B is the exact location of this sample in its modern geographic context in the Appalachians in the eastern US. And just for orientation's sake, for this paleogeographic reconstruction, the yellow star in the bottom near the Antarctica, proto-Antarctica, is the South Pole. So these land masses in this island arc, this back arc volcano system, was in the tropic latitudes. And so processing this sample from Red Mountain Expressway, the star of the show is really the zircons. So in order to get the zircons, we had to crush the ash samples, and then we sieved to get grain sizes that were compatible with the eventual magnetic separation techniques that we use with the Franz magnetic separator. And so anything smaller than 32 microns of grain size would not be affected by gravity enough, and the grains wouldn't separate properly. And anything too big, gravity would work too well and the magnet wouldn't separate things properly. So between 500 and 32 microns was the sweet spot for this analysis. And after getting those grain sizes, we put the minerals in heavy liquid, sodium polytungstate heavy liquid density separation. And so since zircon has a density of about 4.6 to 4.7 grams per milliliter, when it was dropped in sodium polytungstate with a density of 2.8 grams per milliliter, it sank and the lighter minerals floated. And so we got rid of anything that didn't sink, and then we passed it through the Franz magnetic separator. Zircon is not magnetic, so all the magnetic minerals were then separated away, and we were left with heavy non-magnetic minerals that were then hand-picked to pick zircons out of this sample with a wet fine-tip paintbrush. They were mounted onto double-sided tape and placed in an epoxy mold, and then that epoxy mold was filed down to expose the interiors of the crystals so that we could send them for analysis at the Lasercron Center at the University of Arizona. And so this is a mount map. The picture on the right is the mount map of these prepared samples. The rims associated with the volcano and the melt from the Taconic orogeny are denoted by the green arrow surrounding the inherited core, which is from previous exhumation and crystallization. So we sent them to the Arizona Lasercron Center for uranium-lead geochronology and lutetium-hafnium geochemistry studies, and they did this through laser ablation techniques, and the ablation spots were pre-selected and then sent to Lasercron, and then they zapped our crystals for us. And this is what we got back from them for the uranium-lead geochronology work. On the left is a graph of all of the uranium-lead ages of the zircons. But for our purposes, we wanted to be a little bit more precise and narrow things down. So the concordant within 85 to 115% age of the Taconic rims, which is the cluster around the very bottom left of the first figure, and it's more zoomed in on in the middle figure, was 446 plus or minus 2.2 million years old. And the inherited cores, again concordant within 85 to 115%, there was a major cluster, and this is the figure to the right. There was a major cluster around 1.0 to 1.1 billion years old, but there were notably some as old as older than 1.6 billion years old. And the lutetium hafnium data, the taconic rims, again 446 million years old, right past the 400 million year old mark on the plot to the left. They plotted in negative epsilon hafnium space, so they had negative epsilon hafnium values, which are indicative of enrichment from crustal sources. And the inherited cores, we had a few plotted in negative space, but then a good bit of them plotted with positive epsilon hafnium values. And then the figure to the right is the same figure, just with a third dimension, and that third dimension is just the intensity and sort of the frequency of values with respect to the other values. So since there were so many samples that plotted together with the taconic rims, they have that noticeable peak. And so the uranium-lead dates, the ages that we got for the Deicke zircons, are notably younger than in previous studies by several million years. And so this could be the result of erroneous measurements or issues with the methodology. But out of the 3 standards that were used with this study, 2 of them came back on the mark and were very accurate. So it's unlikely that the ages could be that far off, but more studies at different universities with more samples could sort of close this disparity and address this gap in the age. But if the age is accurate at this location, then this could shift the faunal transition of the conodonts B. compressa and P. undatus in the Tyrrhenian North American stage of the Ordovician, of the Upper Ordovician. And it also could shift the Tyrrhenian Chatfieldian boundary with the North American Ordovician stages. And so if the Deicke is younger than we think currently, then it would essentially shift these thresholds more recently than what we thought. And the lutetium hafnium geochemistry showed us that the negative values of the taconic rims were enriched from the rims and the inherited cores were enriched from crustal contamination. And the vertical dispersion of the rims within their negative hafnium space was indicative of the introduction of depleted mantle material into the taconic melt within the crustal column of the overriding plate. And the inherited cores with the negative values suggest that there was some recycling of detrital zircons which were previously enriched. And the positive epsilon hafnium values of most of the inherited cores are characteristic of the juvenile depleted mantle material. And so essentially these inequalities, if you sort of bolster this ratio and you enrich the hafnium, then as the denominator of this ratio grows, then you'll drop below the chondritic uniform reservoir, which is the 0 line on the axis on the previous plot. So the CHUR, the chondritic uniform reservoir, as you increase the denominator, it'll drop below. But if you decrease in the denominator and you extract hafnium out and you deplete the ratio of hafnium, then you'll end up in positive epsilon hafnium space. And so the implications this has for the tectonic setting and the model that's used to describe it. So the back arc Sea of Japan model, we would expect to find positive epsilon hafnium values from a more direct mantle extraction. And in the accretion of arc Timor model, you would expect to find crustally enriched contaminated melt caused by the extraction from underthrusting plate. And so the previously enriched material slipping underneath this island arc in the Timor model would be the source for these enriched detrital zircon inherited cores. And this is the model that was created based on the previous Timor model, but this sort of displays the process that would have created the relationships of uranium, lead, and lutetium hafnium in the zircons that we find. And if you follow the green arrows, that summarizes the path that was taken by the detrital zircons down through the subduction zone, and they were extracted from the underthrusting plate, mixed with depleted mantle material from the upper mantle, and they were mixed within the crustal column of the Taconic island arc. And then the zircons and the melts that came out of that were zircons with 446 million year old taconic rims, with enriched 446 million year old taconic rims, and 0.8 to 1.6 billion year old, a mix of depleted and enriched inherited cores, which were then erupted back out to the surface and deposited on the Laurentian continent in the form of ash. And so looking at this arrangement from particularly right to left, the Iapetus Ocean and transitioning into the Taconic island arc with an accretionary wedge built up from the scraping of the underthrusting continent between the carbonate platform and the island arc. This is reflected in the present lithologies and facies in the eastern United States, where from the bottom right of this figure, there's the Iapetus Ocean bordered up with the Taconic highlands, and then between the Taconic highlands and the large carbonate platform, there's a noticeable sliver or packet of sandstone claystone facies, which are evidence of this accretionary wedge that was created from the scraping of the underthrusting continent. And so as supporting evidence of the Timor model, we have the lutetium hafnium data. It supports enrichment and suggesting the mixing of depleted and recycled material in the crustal column. The Ordovician lithologies and facies across the eastern United States, which reflect this relationship and structure of this boundary, of this model, and the accretionary wedge created from the scraping of the underthrusting plate could have driven, and the increase that it would have caused in sediment load on the basin would have driven a deepening of the continental shelf basin, leading to the Gutenberg isotope carbon excursion, which saw a shift in the carbon isotopic composition of the carbonates on Laurentia, going from more tropical carbonates to temperate carbonates, as seen in the figure to the right. This could have worked in conjunction with the extensive volcanism that is associated with this orogeny, as seen by the Milbrig marking the boundary from the tropical carbonates and the temperate carbonates. And the issues that the Sea of Japan model faces when, in light of this data, are that the lutetium hafnium data for the Taconic rims don't agree with the expected values that we would have gotten from a back arc setting. And the buildup of the sandstone facies in the Appalachian Mountains, it would have been created primarily and almost exclusively from the erosion of the Taconic highlands, which doesn't provide a substantial or adequate source for the amount of siliciclastic accumulation that is created from and that's observed in the lithology today. And the lack of an accretionary wedge would have left volcanism as the primary driver of the climate cooling during the Ordovician and the Gutenberg isotope carbon excursion. But this isn't supported in the geologic record, as the Deicke eruption didn't have significant impacts on global climate or any major extinctions or transitions in lithology. I would like to acknowledge and thank everyone in attendance, in person and on Zoom, my family, my friends, my fiance for listening to me talk about this for the past several months. Mr. Andrew Webb and Mr. John Kerningham, who did all the hard work as far as sample preparation whenever I was still wanting to do a project on a dinosaur femur. They were processing all these samples, and I kind of reaped the benefits of their hard work. Dr. Matthew Locke for imaging the samples that were sent to the Lasercron Center. Dr. John Haynes and Dr. Adam Forte for their guidance and contributions to this project, especially Dr. Forte with the insights on the hafnium data, and Dr. Haynes for all of his previous literature that I've explored through the course of this thesis, and specifically for his agreement to join us at 10 p.m. time in Italy for this, and Dr. Akram Herman for his mentorship, advisement, and commitment to this project and to my academic success and future career. Thank you.